All right. So we will talk about a software in the loop environment and how it can accelerate control development, as well as how it can help black box type software sharing. Here is a brief outline of what we will talk about. So first, I will give a brief outline of what SIL environment means. Then I'll give an example how it can be helpful. Then I'll go over the objectives for the work that we're doing. And then I'll talk about code segmentation, which is really important to be able to use the SIL environments. And then I'll talk about two libraries that we build for UNIFI. One is the SIL Wrapper environment, and the other one is a grid forming code base that we also built for UNIFI. Then I'll show a lab demonstration, which actually goes into the detail of how we can use the two libraries together. And then my co-presenter will take over and he will show a number of use cases, again, showing how you can use the SIL environment in different type of applications. So first, before going into what a SIL environment is, first let's talk about the usual environments that we use when we are trying to develop a new controller. First one is obviously block-based control implementation. This is very easy to do. We do this all the time. Takes very short amount of time to build. Very intuitive, but the obvious drawback here is that this does not really represent the actual software that you use in your power electronic hardware. Then you have another option that you can use. For example, if you're using Plex environment, you can use C script, or if you're using PCM environment, you can use a C block, where you can integrate very simple C functions in your simulation. That improves it a bit, but you still cannot really use the actual software base or the actual code base that you will program into your power electronic hardware. All right, so then what SIL does for you is that the same software files or the same software code base that you are using to program your control hardware in your actual power electronic system, you can use the same files to run your simulation. So that's what SIL environment is. So if you have a system like this, what you can essentially do is it becomes pretty easy to share your software with somebody in an external institution as a black box. And this also makes it very easy to add, let's say, more than one power electronic system in the same simulation file. That means you can have 2 or 3 IBRs in the same simulation, and that can be done very easily. And with all of this, obviously, this will accelerate your control development. Now I can give an example how this SIL environment can be very useful. So this is an 1 MVA solid state transformer, which is being built at NC State. And this will be used as an EV charging station. The input to this system is around 13.2 kV. The output is around 800 volts. In terms of power, it's not that big, but the system is quite complex. As you can see on the left side, in each phase, we have 5 of these blocks. And inside each block, we have a dual active bridge. And it has its own completely local controller, and then there is an active front end. And all the active front ends of the whole system, they are being controlled by a centralized controller. So now you can think of this in this way, that this is structurally very close to a group of hierarchically controlled IBR systems which are tied to the grid, where you have a centralized controller dictating or dispatching some set points, and you also have some local controllers as well. So in the lab, this is how the system looks like. So inside this cage, we have the SST. This is the load. This is the feeder transformer that gives us the medium voltage feed. Then here is sort of an SCADA interface which we can use to talk to the system itself. In terms of control implementation, what we are doing, the central controller is implemented in an FPGA system on chip, which is shown here. And then the local controllers, they're implemented on TIDSPs and all of them. So basically we have 15 TIDSPs implementing the local controllers. And all of these control chips, they are tied in a loop through a communication interface. So when somebody is working on the central controller side, they are using the SDK, the software development kit, to write code and compile it and test it in the hardware. If somebody is working on the local control of the DABs, then they're working on TIDSPs and they're using Code Compositor Studio as the interface. Now, one of the challenge was that some of the software that we have that has to be portable. That means that has to be used on both TIDSP as well as on the FPGA. The FPGA has a dual core ARM CPU, so that's why we run the control software. Now, to make things a bit more complicated, the effective PWM rate that we have that goes up to almost 100 kilohertz, and that makes it almost unfeasible for us to use the real-time control hardware in the loop platforms. Then the hardest issue for us was that multiple students are working on the same system, but on different parts. For example, if student A is working on, let's say, on the central controller, then he goes into the lab and does some programming. He tests it in the hardware, and then when he's happy, he will push that into GitHub. Let's say that part is okay. Then student B comes in, he writes something for the local control of the DABs, and he does some test in the lab. When he is happy, he will also push that into Git. Now, a third student, he comes in and he wants to check if the different parts of the system, they work well together or not. Now, although he has access to the software that both student A and B wrote, but he doesn't really have the time or doesn't really want to understand what those softwares are doing. And he definitely does not want to make a block-based implementation of that control software in his simulation environment to check how the different components are doing together. Then this becomes a big problem, how we can accelerate this whole control development, and how do we test it. That's why I started on this SIL work, and then eventually it turned out to be like this. So let's say we have many students working on different parts of the system. So when each student goes to the lab and writes some code, that part is tested independently. And when that is done, that is pushed to the Git. And then all other students, everyone is doing their own thing. And when all of that is completed, then in the SIL environment, we pull all that software, all the different softwares from Git and run in the simulation environment. So basically, instead of using a block-based controller, all the different softwares are being directly used by the simulation environment. So that's how this whole thing works now, and that made it very easy for us to go through the iterations, go through the different stages of the control software. So that's how SIL can help you to accelerate your control development. But that's not all. There are other applications where SIL can help you a lot. For example, let's say if you are a system integrator and you're trying to develop a plant level controller for a plant where you have IBRs that came from different vendors. So let's say each vendor has their own way of doing things. Now, how do you get all of their control and evaluate if they're working well together, as well as working your own controller that you're trying to make? So now the question is, how do you evaluate that before going to actual field? How do you simulate that all together? And the same thing can be said if you are, let's say, a system operator, and you're trying to evaluate a network where you have IBRs that came from multiple vendors. The same thing can be said here. How do you evaluate? How do you do a EMT type simulation without the model that came from the different vendors? So for doing all of this, we really need a way to do software sharing as black boxes, so that different softwares coming from different vendors, they can be simulated together, or they can be evaluated together. So with all of that, if you are convinced that SIL is something good and we should have this for control development and evaluation, now let's take a look at something that we really need to be able to use SIL platforms, which is code segmentation. So what I mean by code segmentation is, if we look at a typical power electronic application, we can create these layers. These type of layers are always there. So at the very bottom, we have the power stage. On top of that, we have the firmware. So what do I mean by firmware? So firmware is the part of your control code which is specific to the control hardware platform that you're trying to use. For example, if you're using a TI DSP, when you program the ADC, the analog to digital conversion, that code is specific to TI platform. So if you switch to a different microcontroller or an FPGA, then that has to be done in a completely different way. So PWM, ADC, these type of stuff, they are specific to the control hardware platform. So that's what we call the firmware part of your code. On top of that sits the software part. So the software part is something which is completely independent of the control hardware platform that you're trying to use. And ideally, the software should be completely portable across control hardware platforms. So ideally, you can take a piece of software from an application where you are using a TI DSP, and you should be able to use that identically in an application when, let's say, you are using a ST microcontroller. So that's what software is. And then in any application of a substantial size, you always have this outer layer. This can be a user interface or a SCADA interface through which you should be able to dispatch set points such as PQ bias or droop parameters. And as well as you should be able to monitor what the hardware is doing in real time. So that's the outer layer. Now, in very hyper applications, this type of segmentation that happens inherently. And what do I mean by that is, let's say if you have a multi-megawatt system like this, what you end up usually doing is that your firmware is implemented typically using an FPGA. And then the software part that is implemented in a, let's say, a soft core or a hardcore CPU. But if you don't have that, then you will have to make an effort to ensure this. Now, if you have the code segmentation, what you can do, let's say in MATLAB Simulink environment, if you model this power electronic converter and you implement these different layers, the firmware layer, the software layer, and the outer layer by different blocks, if you have an SIL platform, what you can do, you can actually replace the blocks that you're using to emulate the control by an SIL block. So this software in the loop block, what this block does, this block actually lets you to use the actual software code that you will be programming into your control hardware in your simulation directly. So this block is the link between your simulation and your actual software files. So this block will bring in the softwares in your simulation environment. And this is actually a block that we built for UNIFI, and I will talk about that in the later slides. So what I said in the earlier slide that in your application, if this code segmentation is already there, then that's very good. But if not, then you will have to do it yourself. You'll have to ensure that your code segmentation exists in your application. For example, in an application where you only have TIDSP, then chances are that all of your software and firmware, they are in the same code files, and you should make an effort to say, to basically segment them in the right way. So if you have that, then you can use these blocks that we created for UNIFI. So what this does, you can use or you can take these files that we created and you can install this in your MATLAB environment. And when you have that, you should see this type of block in your system. And it has this IO blocks, the input-output structures that you need to implement the control. For example, if I go back here, this control software, it needs to have the feedback from your power stage. It also will do all the control action based on the feedback that it gets, and then it will give you some control outputs. At the same time, it will also be able to take set points from the outer control layer, and it will also let the outer control layer know what is going on. So these type of input and output structures you always need. So the library that we created, that has those options. So you have the control output and feedback structures. You also have the dispatch parameter and the status monitor structures. At the same time, when you are doing this test, you also need an option to basically debug. So that's why we also added debug input and debug output structures, which you can use to probe into what is going on in your control software when your system runs. So that's not all. This block also lets you do to specify what are the different task groups. And what I mean by task groups is that when your controller starts up, so let's say in your real application, when your controller starts up, you need to do a number of things, some very specific things, which we call the initialization tasks. And these tasks should also happen when you start your simulation. But then there is the highest priority control update task. So that can happen at the low to high edge of this input to the block. And then you can have as many background tasks as you want. And in the background task, you may do something like talk to the SCADA interface or do some slower rate control updates. And the nice thing about this block is you can add as many blocks, as many background tasks as you need. And you can also specify what is the update rate for each of these task groups. And one more thing to note here is that when you implement your control in a discrete time way, there is always this control implementation lag. And the way this block is implemented, it will enforce that control lag is always there. You don't need to worry about explicitly emulating that in your simulation. The block will always do that by itself. So with that, now let's take a look at how you can integrate white box software and black box software. So what do I mean by white box software integration? So let's say you already have access to the actual C code files that you will program into a power electronic hardware. So if you do have access to the actual software code base, you should use a block like this. So the library that we created for UNIFI, it has two blocks. The first block looks like this. As you can see here in the block, it says external C. So what this block does is it lets you link an external C code base into your simulation platform. And it also guides you through the steps that you must do to integrate that code base into your simulation environment. But what happens if you don't have access to the external C code base? Then you should use this block. And as you can see, this block, it says MEX. MEX is the short form for MATLAB executable, which is a binary file. So the idea is that the guys, or let's say somebody has access to the actual external code base, they should create a MEX file using the first block, and they will give that to you as a binary executable file, as a MEX file. And then even though you yourself do not have access to the external C code base, you can only use that binary executable file in your simulation environment. So that's how you can link a black box software into your simulation environment. And to guide you through the installation of these blocks and how you can set these up, we also wrote a user guide that has the details how to do all of this. Now, to reiterate how the black box software sharing can happen. So let's say you are in institution 1 and you want to share your own control software with an outside institution, institution 2, as a black box software. So what you do, you use the first block, which looks like this. As you can see, it says external C. So you use your code base and use these blocks and create the MEX file. Once you have that, you share that MEX file with the institution 2. So you basically send them that binary executable file or .mix file. And then who is somebody in institution 2, they uses the other SIL block, which looks like this. As you can see, it says mix here. And they can take that .mix file and run their simulation using this block. So that's how you can do black box software sharing. And if you are in institution 1 and you are trying to be even more careful and you don't even want to let institution 2 know what is the update rate of your control software, you can also do that. But I'll not get into the detail of how that would work. But if somebody is interested, we can definitely talk. But now let's talk about the other thing that we did for UNIFI, which is a grid forming control code base. And this code base is done using C. So the structure actually looks like this. So what we have is an inner current control loop, then a virtual admittance loop, and then on top of that sits the synchronizing controllers. This code base uses floating point math, and because this is a software code base, it is completely transferable from one control hardware platform to another. So basically, you can use TID, SPS, ST microcontrollers, or FPGA socks, whatever you want to use, it should work. And then for the synchronizing controllers, you have different options, actually 4 options. You can use Droop control, you can use VSM, so basically virtual synchronous machine type control, or you can use virtual oscillator based control. To be more specific, UVOC or DVOC, which are structurally very, very close. So you can use any of these. And the nice thing about this is when you're trying to change from one type of control to another type of control, let's say you are trying to use either Droop control or UVOC, you don't need to change anything in the code. You just need to change a compilation, a compiler flag. And when the compilation is done, the code will automatically adjust everything to use the right type of control that you want. All right, so with that, the other thing that I want to mention about this code base is that it's done in a completely modular way. That means you can pick and choose which layer you want to use. As you can see, there are different files. So these are the compensators, these are the primary control, then transformations, vector control. So you can pick and choose which layer you want to use and which one you want to write your own. That can be done. And the other thing is par unitized. So the the whole code base is done in fully in a parentized sense. That means you can parameterize your control parameters on a through per unit quantities. So that makes it easy for you to adapt to your needs. So let's say you're trying to change the rating of your system, the voltage rating or the power rating of your system. You can do that pretty easily. So with that, now I will actually show a pre-recorded video where I will actually talk about how you can use both of this SIL library and the grid forming code base together to evaluate your controller. So in our hardware test platform, we are using TIDSP as the control hardware. So what I have done, I have taken the code library that I just showed, and I have integrated that into a Code Composer Studio code project. This is the top level firmware source file that you see. So this firmware source file actually calls the different control and background tasks from the software side. And some of the files from the software side you can see here. So this is a file where a user can actually define the rating of the inverter. This is where you will define the control gains, and everything is per unitized here. And there are other files such as this one. Here you can look at the different implementation of the synchronizing controller. So we have three options here. One is the group control, another one is the virtual oscillator based control, and then the third one is virtual synchronous machine type control that you can see here. You can take a look here. So for this particular experiment, I am going to use group control, and then the interface file actually defines the interface between the firmware and the software side. So here I am defining what is the initialization task, what is the PWM rate control update task, and what is the background task. These are coming from the software side. Before we run it in the hardware, we will first run it in the SIL environment. Here we have the power stage over here. So this is the 2-level 3-phase bridge. This is the LCL filter. This is the grid. This is the firmware, but we do not have the control block or the software in here. To link the software to this model, we go to the library browser, and if you have already installed the UNIFI SIL library, then you should see these two blocks. Because we are trying to link the white box external code base to this model, we will use this block which has the max builder. So we drag and drop this block in our model. We name it. Then we'll have to go through the different steps to link the external code base with this model. But before doing that, I'll break the link of this block to the library because this uses self-generated code. All right, so now we can go through the steps. So in the first step, what this block will do, it will create a bunch of scripts that it has to run in the backend when it does the mix building. So these are the scripts that will run in the backend. So before going to the second step, I'll have to link the external code base with this model. To do that, first I go into the interface.c file, and I will copy and paste what we have done for the actual hardware implementation. So I copy this and I paste it here. Save it. Then the other thing I need to do is I need to tell the compiler where the different files are. So I need to add actually three things. The first one is I need to tell the compiler where are my header files. So I need to add the include path. I need to add the source paths. And also I need to add the different source files that the compiler should use. So the first one is to find out the location of my code base. I go to here, I find out where my codes are, then I will link this here.
Now that my code linking is complete, I can get back to the rest of the steps. All right. So the next step is update the interface dimensions. I do that. Once that is done, then I configure the mix builder. And then the last step is to actually build the MATLAB executable file. And after this step, you can see that in the working directory, there is a mix file named after the block name that you chose. All right, so the mix file has been built. You can run the simulation now. Now you can see the simulation runs using the external code as the controller. Now you can see that the inverter actually is tied to the grid and start to operate at this instant in time. Before that, the inverter goes through some pre-synchronization stage, and that's why you see this large oscillation in the real and reactive power output. And these are all virtual. So the actual inverter operation is starting from here. So now that we have verified that the code runs, all right, now we can move on to the hardware experiment. Now I'm loading the code into my hardware, and then I can start the experiment. All right, so I'll start the experiment now, and I will switch to the scope screen. So when I turn on the converter and tie it to the grid under a steady state condition, the waveforms look like this. So at the very top, you have the DC bus voltage, and then you see the three-phase line-to-line voltages, and the very bottom you see the three-phase output current of the converter. Now I will introduce a three-phase fault or a three-phase voltage sag by the grid emulator, and this is how it looks like. So if I zoom in on this, then you will see how the converter responded when the fault was introduced, and when the fault was cleared, it immediately went back to normal operation.
All right, so this was done in the hardware setup that looks like this. So basically, we have a three-phase inverter, and then there is a grid emulator that we use to emulate different grid events. We also have some external inductors which we can use to emulate different short circuit conditions, and then there is also a battery energy storage system to basically maintain the DC bus. So that's what we used for the experiment that you just saw. Now I will hand over to my co-presenter who will talk about some use cases of these two libraries that I just talked about. So I will stop sharing my screen and so that he can share his screen.
Thank you, Awal, for the introduction to the SIL library. And I am Rifat Kaisar from NC State University. Now that my partner Awal has given an introduction to the SIL toolchain altogether, I will talk about a few of the use cases that we are hoping to use it for. The first one is for a network level simulation. For that, we have chosen the IEEE 13 bus system. It's the radial distribution network with majority of the line rated at 4.16 kV, but it also has a short 480 volt segment located on the feeder node 634. The line models are designed as pi line segments. And also, as for the load, it has a mix of balanced and unbalanced loads. The objective is to evaluate the impact of GFM inverters through network level simulation. And how the SIL environment can help us with that, I'm going to talk about next. So this is one example. Here we can see that we have a subsystem block over here, which contains the whole of the IEEE 13 node test feeder and giving access to the 634 node, the node number 634. As you can see, two of the inverters are connected in parallel to the same node. Now, one good thing about the SIL toolchain that has been developed is that within the same simulation model, we can have multiple of these SIL blocks or the wrapper blocks. As you can see here, we have two individual wrapper blocks dedicated for controlling each of these inverters. Now, one of them is termed as the white box code. This is because this is using a wrapper block which can link to the external C code base, whereas the second one is only using the MEX file coming from a separate vendor. So that's why you call it the black box code. And this toolchain actually allows us to run two separate inverters running from one from a custom code and the other from a MEX file simultaneously. And then it allows to study the parallel connected inverter operation in a distribution network. The second scenario that I'm going to talk about is like this, where again, we have a subsystem that contains the whole of the IEEE 13 node test feeder, but now the two of the inverters are connected at two different nodes. Again, we can have one white box code from one vendor and the black box code from a different vendor, and use the two different wrapper blocks for running these two inverters. This kind of simulation study will allow to evaluate the scenarios where inverters are connected across the distribution network. Moving forward, the SIL library toolbox, we are also envisioning it for using to evaluate the UNIFI middle layer evaluation. So the UNIFI middle layer is currently under development, is going through the development process, but once it is finalized, as far as our understanding, this middle layer control, the middle layer control will sit between the external outer layer or the SCADA system and the vendor proprietary control layer. This will receive the dispatch parameters from the SCADA layer or the outer layer and translate it through some intermediate dispatch signals to the vendor proprietary control layer, so that it can ensure that the inverter itself is maintaining or fulfilling the UNIFI specification requirements. Now, again, like I mentioned before, within the same simulation block, we can have multiple of these wrapper blocks. Now, one of them can be dedicated for evaluating or emulating the UNIFI middle layer, whereas the second one can emulate a vendor proprietary control. This kind of simulation will help to evaluate the UNIFI middle layer with a wide range of GFM control architecture. Moving forward, this is the same hardware that Awal was showing earlier and has been used by us for doing the lab demo. Now, we also envision it for using this hardware test bed across the consortium. And the wrapper simulation environment can actually help us to do that. For now, what we are doing, we evaluate any of the control development in the SIL simulation environment before implementing it on the hardware. But any of the control software developed outside NCSU can be verified in this C wrapper environment first. It can be a white box type of wrapper code evaluation, or the external institution can share their black box code with us. But once it is validated through the wrapper simulation, this will give us confidence to use it on the hardware directly, and this will essentially facilitate to use this hardware test bed across the consortium for validating different control architecture. Moving forward, the three-phase VSC converter network system that we built is based on some modular PCB boards, and we have two such inverters built within our lab, which essentially constitutes the multi-inverter test platform. This allows to evaluate two different primary level GFM controller on these two different inverters and investigate their interaction through hardware experiments. But again, the SIL environment actually helps to evaluate this before going to the hardware experiments directly. Here we can have one custom code coming from us, and then a second institution can share their code base with us, so that we can run the simulation and evaluate the control interaction and the dynamic response preliminary through the through this SIL wrapper block environment, and then adopt it in the code in the experimental platform for validating their performance. Moving forward, the last use case is that We are also hoping to use this for the UNIFI specification testing, or to at least assist the UNIFI specification testing. Here, because these voltage source converters are fully programmable down to the switch level, we are hoping to have this back-to-back inverter test platform. We already have the transformer, and the plan is to connect 2 such VSCs through this transformer, where one of the VSC will have the code, or it will behave as the grid emulator or the UNIFI spec tester, and the other VSC can have any custom GFM converter control architecture. And then through this experimentation, we can validate whether a particular control architecture is meeting the UNIFI specs through experimentation. And again, this SIL simulation tool will actually help to build this model first, and then test it out in the simulation and look at the interaction first before implementing it in the hardware test platform. So these are the couple of the use cases and the simulation demo models that we are working on, and hope to use these wrapper blocks for validating different control architectures, as well as evaluate a wide range of inverter operation scenario before transferring them over to the hardware test platform for further validation. With that, I will stop my presentation and hand it over to Awal for wrapping up the presentation today.
Thank you. So I'll again share my screen. All right, so until this point, all we have been talking about, everything was happening in MATLAB environment. But in the industry, there is a much bigger problem in the context of what UNIFI is trying to do. For example, let's say if you are a system operator and you are trying to do an EMT type simulation in PSCAD, and the network that you're interested in that has the IBRs from multiple vendors, and every company has their own environment, own tool chain. So let's say in one company they are using MATLAB, but they are using SIL, but another company they are again using MATLAB, but they're using MBD. So which is basically model-based development, where you start with block-based control implementation, and then you auto-generate your code from those blocks, and you program that code into your hardware. But then some other vendor might be using Plex. Somebody can use the PSIM or any number of environments to develop their code or to evaluate their system in a simulation environment. So how do we take these heterogeneous environments or models that came from this heterogeneous environment and put them all together in a simulation environment where you can basically simulate large power systems? So that's the big problem. We definitely need a way to share the softwares or the models as black boxes, but also we need a way to do model export or co-simulation across simulation environments. So how can we do this? One way that we may think about is something called a functional mockup interface. This is something that started in Europe. And initially it was aimed at automotive embedded systems. So what this is essentially is a standardized interface or a way to do model export or co-simulation across simulation environments. And an example of this, I found a pretty nice example which actually applies to exactly what we are trying to do. So this is a work that was done by a group at Delft University of Technology. So what they were trying to do, they export their power electronics controller model from MATLAB environment with an standardized interface, which is this FMI, functional mockup interface. And the model that they export is called an FMU, so functional mockup units. And this can be completely black box. And the nice thing about this is that it does not only need to be from MATLAB, you can have these FMUs that can come from other simulation environments as well. And they can basically link it with PSCAD. But one thing is that PSCAD already has a way to do co-simulation with MATLAB, but my understanding is that that can become pretty slow if you are trying to do data exchange at a very high rate. But this group, what they stated that using this standardized interface, the simulation using AFMI that took almost the same amount of time as doing the simulation solely in PSCAD. So this is something that we can look at. So ideally, what we could do here is that the SIL models that we showed in the earlier slides, we take that control software and we also take the power stage and convert that to a set of ODEs. So basically, the whole IBR becomes a FMU. And we export that to basically do core simulation with PSCAD. That is an idea that we can explore probably in the UNIFI ModSim group. But with that, I'll just go briefly over what we have done in this work. So we created a SIL platform to be used in MATLAB environment. We also created a user guide that will guide you through the installation and how you can set it up for your own simulation. Then we also made a grid forming control code base, which gives you the option to use droop control VSM or virtual oscillator based control, UVC or DVOC you can use. We created a bunch of demo models that shows how you can use both of these this library and code base together. And we also showed some use cases, how you can use it in different applications. And at last, about the next step. So we have a bunch of planned activities. So with respect to the SIL environment, this is something we are planning to do. So all that we have shown here, there was an assumption that you are essentially doing a fixed rate update of your control software. You can also do a variable update rate using the same block, but that becomes a bit slow. So your simulation can become a bit slow if you're doing that using the blocks that I showed in the earlier slides. So there is a way to improve the speed. That's what we do for our internal use, because at very hyper applications, let's say 5 or 10 MV applications, in most cases when we're using IGBTs, the PWM update rate is not fixed. And to do that, we basically use a block scheduler, which uses MATLAB S function-based app environment. So we're planning to add that to the UNIFI SIL library in the next few months or so. And then we'll always make sure that the demo models that we create, they always work out of the box with both the SIL library and the GFM control code that we will share. And in terms of the code library, what we are planning to do, our ongoing R&D activities that we are doing at NC State, we will continually integrate those new findings with this code base. And if there is a need to have more or other kind of synchronizing controllers on top of the 4 types that I showed, we can definitely look at integrating that in the code base. And we will probably make a short user guide for the code base as well. For example, how you change the rating of the converter, how you can basically parameterize the controller and such. So that is the planned activities, and some other opportunities. We do not have any specific plan on this, but something that can be looked at is one thing that the SIL wrapper does right now is that it only works with external C code base, but we can look at how we can add support for languages other than C, for example, Rust. It can be done that we can have the compiler support for the UNIFI SIL block to work with Rust. And the last thing that I talked about is how can we take the SIL modules with the control software and the power stage and create a FMU block so that we can take it from MATLAB environment and integrate it in a PSCAD or some other simulation environment where you can basically simulate very large power systems. So that is something we can explore for sure. So with that, I will stop here. And if you have any feedback, any questions, please go ahead.
All right, Awal